Hi everyone, I'm Amira Shawky, a senior front-end developer in Egypt. I've been working for quite a few years now with building web applications, and lately I have been uh, lately I've been working on some projects that it needed it kept growing with time, and it needed to be separated at some point, and I it was. It had multiple modules. Some were tightly coupled, and others were completely independent. So my focus naturally shifted towards how to scale this architecture. Honestly, I didn't know, but I knew that the solution is revolving around scalability, modularity, and maintainability. So that introduced me into micro-frontends. Micro-frontends offer a way to scale, but uh, but managing state and communication across modules can get really tricky. Because if you've ever worked with micro-frontends, know that where things can get really fun. So what is micro-frontend? Micro-frontends is an architectural pattern and development approach that divides monolithic application code base into smaller applications, each addressing a specific vertical where it's self-contained, independently developed, and deployed. And then these micro-frontends are composed into greater wholes. We all know that a monolithic application usually is a starting point for any new application, whether as an API or a front end. So mainly micro front end extends the principle of microservices into the world of front end. So when do we use them? There are quite few reasons to use micro front end, but mainly we should consider them when we're dealing with large application with numerous functions. As the application grows, it often encounters scalability challenges, and micro front-ends offer a solution by allowing you to scale specific modules independently and ensuring your application remains responsive. We can also use them when it have isolated function sets. This architecture allows you to detach and detangle the different components of your application when you want to minimize the risk of failure. Also, diverse technology stacks. When your application is being developed by multiple teams that uses different technology stacks, micro frontend architecture can accommodate this need perfectly. Each each team working on an independent tool can select the technology stack that work best for you, whether different framework or programming language or libraries. Micro front-ends architecture allow parts of the application to coexist in harmony, even even if they rely entirely on different technologies. Sorry. Okay, micro front-ends have three main composition types, where a micro front-end can be a complete page or also specific fragment of the page, which can be used by other team to add their application, whether it's multiple ways to build. There are multiple ways to build from micro front ends, so let's check the main types to build them. First, we have iframe composition. We have an iframe based front end runs inside its own browser frame, completely isolated in terms of JavaScript and CSS and runtime, meaning no conflict, no shared dependency, and minimal risk of one app breaking the other. This make them ideal for teams when using different tech stack need strictly secure boundaries, or you want to embed third-party or legacy applications. However, that same isolation mean limit that same isolation means that it can limit your application and your integration, such as routing, share state, and consistent theming, become extremely hard to manage when dealing with iframes. But mainly you can rely on browser messaging like post message podcast channel with same site. You can also handle authentication using the same site cookies on a shared parent domain or HTTP only cookie, or for server only, and you still hit modern you still you still hit modern browser limit. For iframe conversion, each micro frontend runs inside its own isolated browser context, which means no shared JavaScript, no shared JavaScript memory, no shared React instance, and no access to parent variables unless you explicitly expose them. So communication here can be a little bit hard and usually happen across window boundaries. Okay, so we can share state here using cookies for authentication, and you can use HTTP-only cookies for the domain or subdomain that you're sharing with them. But for cross-origin iframes, you will need to set same site to none and possibly short-lived token exchange endpoint. Lastly, sharing state with the backend is a source of the truth, where completely forgot to show. Sorry. Okay, you can share state using the backend as a source of truth, where each iframe can fetch the same data and the same API using the shared cookies. So the backend can act as a central store. Second, we have server edge composition, where the integration happens before the code ever runs in the browser. So instead of the browser dynamically loading and stitching together every micro front-end that you have at runtime, server and edge composition does the stitching on the server side or the CDN edge. So right before the response is sent to the user, by merging JSON responses from multiple micro frontends, rendering them before it reaches the client side. So yeah, share state here can be managed centrally, and server controls user sessions, tokens, initial data, and each micro frontend receives contextual props like user info or feature flags from the layout server. You can hydrate those fragments client-side with shared data store like React Query, SWR, or even window initial state. But fragments can't communicate dynamically once they are rendered on the client unless you rehydrate the whole page. So this means no cross-window messaging, no consistent SSR, or so better CSR hydration flow. Okay, for the server-side composition, the backend service act as the layout engine. The shell receives a route, then pulls fragments from multiple micro-frontend services, such as HTML, JSON, template markup. Then it stitches them into a single cohesive document. And lastly, run them fully composed HTML to the browser, so better SEO. Some of the popular ways to do this including purpose-built frameworks like Tyler, Putium, or even custom gateway setups using Next.js middleware or app router. So also we have partial composition pattern like hydration or remix loaders. For the edge side composition, the composition happens on the CDN layer. The edge worker intercept request, which is required micro front-end fragments from your origin, and then stream them into the HTML back from a nearby pub or for faster TTFP with proper caching and keying. This deliver very low latency and allow pre-region or pre-user personalization. So here, you don't share GS state, you share request scope fact and data headers, cookies, payload. So when you keep it minimal, so we need to keep it extremely minimal, signed and cache friendly. So never share secrets such as API keys or tokens, fragments. So you don't, for fragments that you don't fully trust, do server side instead. It also don't share client UI state because it definitely belongs to client. So let's recap. Share only the state that affects rendering consistently and security. That includes authentication, session info, user identity and permissions, localization data, languages, currency, things like that, and the cached backend response. Both server side and both server and edge composition share through context but differ in how the state is stored and managed. For server composition, it runs on the origin near the database, allowing access to sessions, cache, and database. For edge composition, on the other hand, for edge composition, it runs on the TDN nodes. So close to the user and stateless by design. Relying on delivered and cached context like headers, cookies, or value key store. It focuses on low latency, handling lightweight segment-based such as local. Um, that makes it ideal for fast and cache-friendly personalization, but keep in mind, you can't open the database connection, but you can read lightweight state sources. You can use these reconstructed request scope context. This is enough to render or personalize, but not enough to mutate data. So finally, use server composition as your brain. It remembers, updates, and decides. But for each composition, use it as your reflexes, reacting fast using cache knowledge. And always remember, it doesn't own the truth. It acts on partial read-only slice for performance. Lastly, we have client-side composition. Um, Here's a browser is responsive for assembling the final UI by dynamically loading and rendering micro-frontends at runtime. The host application uses client routing to decide which remote components or page to load, where each micro-frontends runs within the same JavaScript runtime and can actually share a dependency, state, and routing context. This model delivers smooth SPA like navigating and shared UX, making it ideal for most applications, literally what we use the most. We have three main types for client-side composition. First, first is web components. Sometimes we don't need a full flag front-end framework like React, and that's where web applications come in. They allow each team to build features as reusable, encapsulated custom elements that can be dropped in any page, regardless of the framework that you're using, or even JavaScript. You can provide that through the Shadow DOM while still running in the same JavaScript context, enabling communication and sharing state when needed. In this example, first one. Okay, sorry. Okay, and the first example, I'm just defining my own tag as a web component called to-do item, and where you can share a little bit of a state to check whether the to-do item is already checked or not. However, web components are less suited for projects that require runtime separation or different frameworks with conflicting dependencies, such using React with Angular or Vue. Or even strict security boundaries. In short, web components for tightly integrated frameworks and agnostic features. Okay. Um, we also have in-page orchestration. Um, this approach lets us load and mount multiple independent application inside the same browser page, each one responsible for its own slice of UI. We have two types for this. First one is route lifecycle mounting. The classic library for this is single SPA. Think of single SPA as a small runtime setting in your browser. It listens to route changes whether the URL matches the registered path. It loads, mounts, unmount the right micro-frontend app automatically. It has three main life cycles: bootstrap, mount, and unmount. And the root configuration looks like something like this. I don't know if you can see it. Uh, where you register an application, and when the user navigates to dashboard, dashboard, the runtime mounts the dashboard application. And when you move somewhere else, it unmounts this dashboard and mounts the next one. So single SPA uses URL-based activation. It doesn't replace your router. It works with them. So each micro front-end can have its own router. For example, if we have team might using React router and another one using Vue router, the root configuration decides which micro front-end to activate using something called active one. When updating one app, it doesn't affect the others. So when you have something like /dashboard /setting, it can load both of them, and both of them can be activated. Each micro frontend can be deployed independently into a CDN and the root configuration only imports them dynamically. That's why companies often use single SPA to migrate gradually when you have legacy work. Um, State here can be shared in a few ways. A lightweight bus event, like sub-dub pattern, custom props that route the passes into each application, also a shared store, um, like Redux, Zustand, that can expose on the window via shared remote module, like module federation, and and the dedicated shared state application using helper packages like single SPA shared. For example, you can create a store in your root configuration and then use this in your micro frontend. This pattern is actually still valid, still right now, even though most teams prefer exporting these these stores through module filtration rather than attaching it to window, which is way better. We know now that how to implement route lifecycle mounting via libraries, but also we can do this for frameworks such as Spiral. Spiral is a framework for building modular front-end application where each module called a pilot is self-contained micro front-end, so each pilot is built, versioned, and deployed independently, often as a separate NPM package or a CDN bundle. Unlike SBA, which is primarily an orchestration runtime, Parallel provide a full framework for building the shell as the host app and building pilots for as micro front-end applications. And it can handle routing, layout, shared state, shared dependency, and some logic also. Each pilot is an independently built and deployed module that register routes, menu item components, or even feature flags into the shell at runtime, just like this example. We can build and publish this pilot as a bundle using ES modules, and Parallel shall dynamically download and integrate it. When using Parallel, we can share state using shared state that Parallel provide via Parallel API, where the shell defines the shared store and or service that Parallel can consume. But also, as a first example. But also, we can define an object of user in the shell, then use it inside our pilot. But we can also share the state using custom API, where the shell exposes it from the pilot as a second example. Second one, where we expose a function that can get us the user object and create an instance of it, where we can consume it in the pilot. Uh, but what if we want synchronization with backend? We have different cases for this. The first one is shared backend, where each pilot can call the same backend if centralized API clients or tokens through a shared viral service such as API.php or something like this. Second type, we can use different backends. We also can, where pilots can talk to their own backend as long as a course is configured properly, and Viral Shell doesn't restrict this. It just ensures the shared libraries and routing remain consistent. We also have cross-pilot state sync. Parallel already offer a lightweight global state container for inter-pilot communication. And for larger system, you can integrate with Zustand. I would recommend it. Also, you can Redux or Recoil at the shell level and expose it to the shared dependency and share the shared dependency. We also have a route page level. In this model, you don't mount entire apps, but rather pages or fragments inside a shared shell that owns the router. So instead of mounting entire standalone application with their own runtime, like single SPA, the host application controls the router and simply loads the correct remote page component when the user navigate. So in this example, the host application owns routing, which is React router, next router, or next router if we're using next. And for each route, it dynamically loads the corresponding remote page from another build or a repo. Then the loaded component render the shared application context. This architecture can be used This is the used architecture like Next.js with dynamic import, module federation inside React router or an X micro frontends or even custom shells. Finally, we're done with n-page orchestration. Now it's the last type of composition and last type of client composition is runtime build sharing. It means multiple applications built independently can share dependency at runtime rather than building their own copies. So we have two micro frontends, dashboard and settings, both import React. They actually use the same instance already loaded by the shell or another application. So at runtime, the host exposes its shared library, and the remote application declares that it expects those shared libraries instead of bundling them. When the remote is loaded, it resolves those dependencies from the host, not from its own bundle. So React is only downloaded once, and there's a single global instance across all micro-frontends. And this introduces us into module federation. Module federation is originally a feature introduced by Webpack 5 and now supported by RS Pack for Vercel, created by Vercel, and many other module bundlers that allows multiple independent builds to share code and load each other modules at runtime without rebuilding or packaging everything together by letting separate application dynamically import components, libraries, or even entire page from from each other while still running on the browser. So how can we implement that? This is an extremely easy code snippet. The host define its remote, load them at runtime, then inject its own version that the remote have asked for. But we need to take into consideration these attributes in the first code snippet. When you have singleton as true, that ensure all micro frontends use the same runtime instance. And for second line, and we have a required version. It's mainly for avoiding version mismatches, which happens a lot. We also have eager as false to load them lazily when they only need it. Notice here that we can expose a store like Zustand, cart information, or even vanilla JavaScript components. And that's it. Just by exposing them, other micro frontends or containers application can use these remote. So how to share state in the client-side component. We can share a lot of things using module federation, whether it's an authentication information, a UI state, or even library, as we mentioned. We can use module federation in a lot of cases, such as route lifecycle, mounting, like dealing with spiral, shared dependency, or single SVA. So we can almost use it everywhere. But single SVA doesn't provide runtime sharing out of the box. You can usually rely on system GF imports, something like import map overrides or manual global exposure like window.react. You can also use module federation and route page level, where hosted and remote pages can share React DOM, and design system where each route is loaded lazily, but they all use the same runtime. Actually, I completely forgot to show these. Also, web component can technically use module federation, but I completely wouldn't recommend this. Since web components isolate execution using shadow DOM in custom elements, you have two main options to handling this with module federation, which is bundle dependency inside each component, or we can also expose shared libraries globally. So web components already provide isolation for isolation and or framework independent. Their strengths come from being independent, comes from their independence, not from runtime sharing or of frameworks like React. We can also share state using custom browser, where events can be used by dispatching events from one micro frontend to another micro. that are interested in the same state that they are sharing. To do this, we need to define a custom event represent the state changes in your micro frontend. Dispatch that event when the state change or occurs in a micro frontend. Dispatch the corresponding custom event using dispatch event method, and then listen for the event in the other micro frontends that interested in that state using event listener. Lastly, update that state when the custom event is received. Update your state. It's important to note that using custom browser event for state management can be complex and error prone, especially when you're dealing with large application and more complex structure. We also can share state by using the browser storage, but we shouldn't store anything and everything in them. We need to, if we're gonna do that, we need to ask ourselves a little bit of questions. Do we need the server to see it on the next request? Yes. Use cookies. It should be only data. It should be only cookies if the data is sensitive, and normal cookies if the client must read it too. We can also ask. Okay. Do we have client-only preference that should persist across tabs? Then we use local storage. Is it per user or per session? We can use session storage, and if it's a cross-site iframe, then avoid using local storage. And you can use boost message or with the server necessarily, but I wouldn't recommend this. And we also have routing and URL, whether it's a VAS params or query params or a hash. The URL is universal contract and the most basic form of sharing parts of the state. So make sure not to share anything sensitive data unless it's encrypted. We also have a shared API utility. It is responsible for caching fetch XOR requests and their corresponding responses, effectively reducing the amount of network requests and improving the responsiveness of the application. All the individual micro-frontends can call the shared API micro-frontend when making a request, giving the API micro-frontend the ability to control whether or not the data needs to be refetched based on the freshness of it. This approach helps minimize the overhead of network requests, improving the efficiency and reducing the risk of error and inconsistent micro-frontends. Lastly, we have exported functions. Let's consider the strategy using a single SPA framework. As we mentioned before, in single SPA, you can share state between different front-end applications by exporting the function from one application to another. As this example, you can define, you can create a shared module that exports the function like in the first application, and then you can import this function and use its instance in the other application. Now we have covered all micro front-end compositions, but we should know there is also some system use hybrid composition where edge serves as a skeleton shell, and client dynamically loads interactive fragments like using module federation. So let's recap everything we have mentioned so far. We need, when we're dealing with micro front-end, sharing data between them need to be as small as possible, such as authentication, user preference, or even feature flags. We have multiple types of state that can be shared, but the main types of them are UI or temporary state, which live inside the micro front-end, but for this, we should keep it managed for each front-end and not share it with the other, so let's keep it as it is. And we also have view or page data page, which is data fetched especially for a feature such as table users, filters, pagination, and this is often isolated per micro front-end unless micro front-end visualize the same data set. And we have global app state. It's a cross-cutting concern for user info, permissions, local, theme, feature flags. This need to be shared consistently to keep the UI in sync. We have authentication. This must be shared securely and often on server side. Lastly, it's server and cache state, which is fetched API responses such as reactive query caches or SWR data or STS payload. They can be shared to avoid duplicate requests and improve performance. And that's it.
Thank you so much.